What is an optical illusion? Optical illusions can use color, light, and patterns to create images that can be deceptive or misleading to our brains. The information gathered by the eye is processed by the brain, creating a perception that in reality does not match the true image. Perception refers to the illusions occur when our eyes send information to our brains that tricks us into perceiving something that does not match reality. The word illusion comes from the Latin word illudere, which means to mock. Some optical illusions are physiological. This means that they're caused by some sort of physical means in the eyes or the brain. The muckband illusion is an example of a physiological illusion. The line in the middle of the picture is one solid color. However, because of how the eye's retina filters the different shades on either side of the line, the right side of the line appears darker, while the left side of the line appears lighter. Other optical illusions are cognitive. Cognitive illusions, such as ambiguous, distorting, and paradox illusions, occur when our brains automatically make assumptions based on the information sent from the eyes. These illusions are sometimes called mind games. Scientists believe optical illusions are possible because our brains are so good at recognizing patterns and seeing familiar objects. Our brains work quickly to make a whole image from separate pieces. How optical illusions work. In a three-dimensional world, our brain receives various clues such as depth, shading, lighting, and position to help us interpret what we see. However, when we look at two-dimensional images, our brain can be deceived because it doesn't receive the same cues. Optical illusions take advantage of this by using color, light patterns, and other techniques to create images that can be deceptive or misleading to our brains. Perception and interpretation. Our brain's interpretation of visual information is known as perception. Optical illusions occur because our brain tries to make sense of what we see and interpret the world around us. Sometimes our brain fills in gaps when there is incomplete information or creates an image that isn't actually present. This can lead to perceiving something that doesn't match reality.
Try out some of these illusions and discover just how tricky it can be for your brain to accurately interpret the images from your eyes. Click on any of the images below to begin your exploration of optical illusions.
Types of optical illusions. There are various types of optical illusions, each with its own unique characteristics. Here are a few examples. Number 1, physiological illusions. Number 2, literal illusions. Number 3, cognitive illusions. Physiological optical illusions. Physiological illusions are a type of optical illusion that arise in the eye or the visual pathway due to the effects of excessive stimulation of specific receptor types. These illusions occur when the eye perceives an abundance of light, movement, color, dimension, and size which can confuse the brain. The overstimulation of the brain's senses leads to a misinterpretation of the image, creating a trick of the eye. Physiological illusions are more complex compared to other types of optical illusions because they rely on overwhelming the brain's sensory processing capabilities. They can take various forms, such as kinetic is different from the images that make it up, while cognitive illusions involve the subconscious part of the brain and how it relates to the image. Physiological illusions are a subset of optical illusions that occur due to excessive stimulation of specific types of receptors in the eyes or the visual pathway. This overstimulation can be caused by an abundance of light, movement, color, dimension, and size, which can lead to the brain misinterpreting the image, creating an illusion. Physiological illusions were not commonly seen in art history until the emergence of the optical art movement in the 1960s. This movement brought attention to the non-representational nature of physiological illusions and their ability to captivate viewers. It's important to note that physiological illusions are distinct from other types of optical illusions, such as literal illusions and cognitive illusions. Literal illusions occur when the image you see is different from the images that make it up, while cognitive illusions involve the subconscious part of the brain and how it relates to the image. Types of physiological illusions. Physiological illusions are a category of optical illusions that arise due to the biological reactions within the eyes and the visual pathway, including the brain's processing of visual information. These illusions can be caused by the effects of excessive stimulation of a specific type, such as brightness, color, position, size, or movement, and can lead to a variety of visual experiences that do not match the physical reality. Here are some key types of physiological illusions. Number 1, overstimulation illusions. Number 2, aftereffects. Number 3, kinetic illusions. Number 4, microsaccades. Number 5, Hermann grid illusion. Number 6, Mach bands. Number 7, waterfall illusion. Overstimulation illusions. Overstimulation illusions occur when our senses are overwhelmed with excessive or conflicting stimuli, leading to perceptual distortions. These illusions can manifest in various ways, such as visual illusions or sensory overload. Let's explore this topic further. One example of a visual overstimulation illusion is the lilac chaser illusion. In this illusion, staring at a black cross in the middle of a graphic can cause us to perceive a green dot moving around the perimeter. Eventually, the pinkish dots seem to disappear, leaving only the green dot. However, this is an illusion created by our brain, as there is no actual green dot, and the pink dots never truly vanish. The lilac chaser illusion combines several physiological phenomena, including the phi phenomenon and the afterimage effect. The phi phenomenon refers to our perception of continuous motion between separate objects viewed rapidly in succession, which was used in the development of early cinema. The afterimage effect occurs when overstimulation of specific cones in the eye tires them out, causing surrounding cones to send opposite stimuli to the brain. In the case of the lilac chaser illusion, this results in the perception of a green dot. Aftereffects illusions. Aftereffects illusions, also known as motion aftereffects or motion illusions, are perceptual phenomena that occur when prolonged exposure to a moving stimulus results in a temporary distortion of motion perception afterward. These illusions are a type of physiological illusion, as they stem from the adaptation and fatigue of neurons in the visual system. The most common type of aftereffects illusion is the motion aftereffect MAE, also known as the waterfall illusion. Here's how it works. Inducing stimulus. The illusion begins with exposure to a moving stimulus, such as watching water flowing down a waterfall or staring at a moving pattern on a screen. This sustained exposure activates neurons in the brain that are sensitive to the direction and speed of motion. Adaptation. With prolonged exposure, these neurons become fatigued or adapt to the constant motion of the stimulus. This adaptation leads to a decrease in the neural response to the specific direction and speed of motion being observed. After effect. When the moving stimulus is removed, or the observer shifts their gaze to a stationary scene, the adapted neurons continue to respond, but now in the opposite direction. This results in the perception of motion in the opposite direction of the original stimulus. For example, after watching a waterfall flow downward, the stationary rocks beside it may appear to move upward. The motion aftereffect demonstrates the brain's ability to adapt to sensory input over time and highlights the role of neural adaptation in shaping perception. It is often used in psychological experiments to study motion perception and the underlying neural mechanisms. Kinetic illusions. Kinetic optical illusions are visual phenomena that create the perception of motion or movement in static images or objects. These illusions can be created through various techniques, such as the manipulation of lines, colors, shapes, or patterns. Here are a few examples of kinetic optical illusions. Kinetic depth effect. The kinetic depth effect is an illusion that creates the perception of three-dimensional forms from two-dimensional images. It occurs when the brain interprets the relative movement of different parts of an image as depth and structure. This effect can manifest independently, even when motion parallax is not present. Rotating tilted lines illusion. The rotating tilted lines illusion is a powerful demonstration of illusory motion from a static pattern. It involves a pattern of rotating tilted lines that create the perception of motion. This illusion can be visually arresting and captivating. Enigma illusion. The enigma illusion is another example of a kinetic optical illusion. It was created in 1981 by Leviant and continues to inspire visual science as well as the visual arts. The Enigma illusion creates the perception of motion from a static pattern and is known for its intriguing and captivating visual effects. These examples demonstrate the fascinating ways in which kinetic optical illusions can trick our visual system into perceiving motion or depth in static images or objects. They showcase the intricate relationship between perception and visual stimuli. Microsaccades illusions. Microsaccades are tiny, involuntary eye movements that occur during visual fixation. Recent research has shown a direct correlation between microsaccades and certain optical illusions, including the Enigma illusion and the rotating snakes illusion. In the case of the Enigma illusion, studies have found that microsaccades can drive the perception of illusory motion. When subjects were asked to indicate when the illusory motion in the Enigma illusion sped up or slowed down, the rate of microsaccades increased before faster motion periods and decreased before slower or no motion periods. Similarly, in the rotating snakes illusion, microsaccades and blinks were found to trigger the perception of illusory rotation. There is a strong quantitative link between microsaccade and blink production and the perception of the illusion. These findings suggest that microsaccades play a role in the perception of motion in certain optical illusions. While the exact neural mechanism behind this correlation is not fully understood, it rules out the hypothesis that the origin of these illusions is purely cortical. Hermann grid illusions. The Hermann grid illusion is a classic optical illusion named after the German physiologist Lorimer Hermann, who first described it in 1870. It involves the perception of gray dots at the intersections of a grid of black lines on a white background, even though no dots are actually present. Here's how it works. When you look at a grid of black lines on a white background, especially when the lines are evenly spaced and aligned, you may perceive faint gray dots at the intersections of the lines. These illusory gray dots tend to appear and disappear as you move your eyes across the grid, and they may also seem to flicker or change in intensity. The illusory gray dots are not actually present in the image, but are perceived due to the way the visual system processes contrast and edges. The Hermann grid illusion is believed to be caused by lateral inhibition, a neural process in which activity in one area of the retina inhibits the activity of adjacent areas. When you look at the intersections of the grid, the visual system perceives high contrast between the black lines and the white spaces, which leads to increased inhibition of the photoreceptors in those areas. This increased inhibition causes the perception of gray dots at the intersections where the inhibition is strongest. Mach bands illusions. Mach bands are a type of optical illusion named after the physicist and philosopher Ernst Mach, who first described them in 1865. This illusion involves the perception of exaggerated contrast between adjacent areas of different brightness or color, especially when those areas are separated by a sharp boundary. Here's how it works. When you look at a grayscale gradient or transition from light to dark, such as a series of gray rectangles with gradually increasing or decreasing brightness, you may perceive dark bands along the edges where the gradient changes. These dark bands appear to be darker than the surrounding areas, especially right next to the boundary between light and dark. Similarly, when transitioning from dark to light, you may perceive light bands along the edges where the gradient changes, which appear lighter than the surrounding areas. The perceived contrast enhancement at the edges of the gradient is due to lateral inhibition in the visual system. Lateral inhibition is a neural process in which activity in one area of the retina inhibits the activity of adjacent areas. In the case of Mach bands, the neural inhibition near the boundary between light and dark regions enhances the perception of contrast, making the darker side appear even darker and the lighter side appear even lighter. Waterfall illusions. The waterfall illusion, also known as motion aftereffect or simply the waterfall illusion, is a fascinating visual phenomenon that occurs after staring at a moving stimulus, such as a waterfall or a scrolling screen, for an extended period. When you shift your gaze to a stationary scene afterward, you perceive an illusory motion in the opposite direction of the original stimulus. Here's how it works. Exposure to a moving stimulus. You begin by looking at a moving stimulus, such as a waterfall flowing downward or scrolling text on a screen. Continuous exposure to this moving stimulus activates specific neurons in your visual system that are sensitive to the direction and speed of motion. Adaptation of neurons with prolonged exposure. These motion-sensitive neurons become fatigued or adapt to the constant motion of the stimulus. As a result, their response to the original motion decreases over time. After effect, when the moving stimulus is removed, or you shift your gaze to a stationary scene, the adapted neurons continue to respond, but now in the opposite direction of the original motion. This leads to the perception of motion in the opposite direction of the original stimulus. For example, after staring at a waterfall flowing downward, stationary objects may appear to move upward. The waterfall illusion is a compelling demonstration of the brain's ability to adapt to sensory input over time. It highlights the role of neural adaptation in shaping perception and demonstrates how our visual system processes and interprets motion information. Cognitive optical illusions, also known as cognitive illusions or perceptual cognitive illusions, differ from traditional optical illusions in that they involve higher-level cognitive processes, such as memory, attention, and interpretation. Optical illusion. It is a wireframe drawing of a cube that can be perceived as rotating in two different directions or flipping between the two orientations. This illusion demonstrates how our brain can interpret the same image in multiple ways. Rubin's vase. The Rubin's vase illusion presents an image that can be seen as either a vase or two faces in profile. Depending on how our brain processes the image, we can switch between perceiving the positive space, the vase, or the negative space, the faces. The spinning dancer. The spinning dancer illusion is an animation that depicts a silhouette of a dancer spinning. However, the direction of the spin can appear to change, with some viewers perceiving clockwise rotation and others perceiving counterclockwise rotation. This illusion demonstrates how our brain can interpret ambiguous visual cues differently. These examples show how our brain's interpretation of visual stimuli can be influenced by various factors, including past experiences, context, and individual perception. Ambiguous optical illusions provide insights into the complexity of our visual processing system and how our brain constructs our perception of the world.
Number 2, distorting or geometric. This illusion creates the perception of a distorted zigzag pattern.
Mueller-Lyer illusion. The Mueller-Lyer illusion consists of two lines with arrow-like tails pointing inwards or outwards. Even though the lines are of equal length, the one with the outward-pointing tails appears longer than the one with the inward-pointing tails. This illusion demonstrates how our brain can be deceived by visual cues such as arrowheads.
Ponzo illusion. The Ponzo illusion involves two converging lines with horizontal bars placed across them. The line that appears longer is the one positioned higher on the converging lines. This illusion exploits our brain's depth perception, where objects that appear farther away are perceived as larger. These examples illustrate how our brain can be tricked into misjudging size, length, position, or curvature due to the surrounding visual context. Distorting or geometrical optical illusions reveal the intricate processes involved in visual perception and how our brain interprets visual cues. Cognitive optical illusions. A few examples. The Shepard tables, created by Roger N. Shepard. The Shepard tables consist of two-dimensional figures that, despite appearing radically different, are identical in their arrangement. The illusion relies on the viewer's interpretation of perspective, as the figures are drawn in such a way that they suggest depth and three-dimensionality. The Ebbinghaus illusion. In the Ebbinghaus illusion, a central circle is surrounded by other circles of varying sizes. Depending on the size of the surrounding circles, the central circle appears larger or smaller than it actually is. This illusion demonstrates how our perception of size is influenced by the context in which objects are presented. The frame lines illusion. This illusion involves presenting lines within different frames or contexts, which can cause the perceived length of the lines to change. Even though the physical lengths of the lines remain the same, the surrounding context influences our perception of their relative lengths. The Ponzo illusion. In the Ponzo illusion, two identical objects are placed within converging lines or railway tracks. Despite being the same size, the object perceived to be farther away from the viewer appears larger due to the convergence of the lines. This illusion demonstrates how depth perception can influence our perception of size. Number 3, literal optical illusions. Literal optical illusions are a type of optical illusion where two different images are compressed into one, creating a perception that differs from the individual images that make it up. These illusions can be created through the use of smaller images that are unrelated to the larger overall image created. Here are a few examples of literal optical illusions.
Mirages. Mirages are optical phenomena caused by the refraction of light as it passes through air layers of different densities. When light rays bend, they create images of distant objects that appear displaced or distorted, often appearing as pools of water or distant oases on hot surfaces, such as roads or desert landscapes. Mirages occur due to variations in air temperature and density, particularly in hot climates where the ground heats up rapidly.
Anamorphosis.
Anamorphosis is a form of distorted projection or perspective that requires the viewer to observe an image from a specific vantage point, or with a particular optical device to see the intended image clearly. Anamorphic images appear distorted or unintelligible when viewed from other angles, but can reveal recognizable forms or images when viewed from the correct perspective. Examples of anamorphic images include street art and paintings designed to appear three-dimensional when viewed from a specific point. Rainbows. Rainbows are natural optical phenomena that occur when sunlight is refracted, reflected, and dispersed by water droplets in the atmosphere, such as rain or mist. The dispersion of light by water droplets separates sunlight into its constituent colors, creating a circular arc of colors in the sky. Rainbows typically appear opposite the sun in the sky and are most commonly observed after rain showers when sunlight interacts with water droplets in the atmosphere. Elephant legs. In this illusion, an artist draws the legs of an elephant without feet and then draws feet without the elephant's legs. However, our brain uses edges to identify objects, so we perceive more than 4 legs in the image. Rocky side of Mars or human face. In this illusion, an image can be perceived in 2 different ways, either as a rocky side of Mars or as a human face protruding from the ground. The image of the human face is created by smaller pieces of rocks and craters, which are unrelated to the human face. These literal optical illusions demonstrate how the physical properties of light can create visually striking and sometimes deceptive effects in our perception of the world around us. Unlike cognitive, image can provide multiple, although stable, perceptions. Some classic examples of ambiguous images include rabbit duck illusion. This illusion, first published in a German humor magazine, Fliegenblätter, presents an image that can be perceived as either a rabbit or a duck, depending on the viewer's focus. Rubin vase. The Rubin vase illusion is a famous example where the same image can be seen as either a vase or 2 faces in profile. This illusion demonstrates how our brain can switch between different interpretations of the same image. These examples highlight the intriguing nature of ambiguous images and their role in the field of psychology as research tools. Ambiguous images challenge our brain's ability to interpret visual information and provide insights into the complexities of perception. Number 2. Composite images. Composite images optical illusions are created by combining multiple images or elements to create a single image that can deceive our perception. These illusions often play with our brain's ability to interpret visual information and can result in intriguing and sometimes baffling effects. Here are a few examples of composite images optical illusions.
Impossible figures. Impossible figures are composite images that depict objects or structures that cannot exist in reality. One well-known example is the Penrose triangle, also known as the impossible triangle, which appears to be a 3-dimensional object, but is actually an impossible configuration of lines and angles.
Hybrid images. Hybrid images combine 2 or more images with different spatial frequencies. When viewed from a distance, the high-frequency components of the image are suppressed, and we perceive a different image compared to when we view it up close. This creates an illusion where the image changes depending on the viewing distance. Anamorphic illusions. Anamorphic illusions involve distorting an image in a specific way, so that it appears normal when viewed from a particular angle or with the help of a special device, such as a cylindrical mirror or a specific viewing position. These illusions can create the perception of 3-dimensional objects or hidden images. These examples demonstrate how composite images can be used to create optical illusions that challenge our perception and understanding of visual information. They showcase the creativity and ingenuity behind these illusions and how they continue to captivate and intrigue us. Number 3. Reversible figures. Reversible figures, also known as ambiguous images, are visual forms that create ambiguity by exploiting graphical similarities and other properties of visual system interpretation between 2 or more distinct image forms. These illusions induce the phenomenon of multistable perception, where an image can provide multiple, although stable, perceptions. Here are a few examples of reversible figures or ambiguous images. Rabbit duck illusion. This illusion, first published in a German humor magazine, Fliegenblätter, presents an image that can be perceived as either a rabbit or a duck, depending on the viewer's focus. Rubin vase. The Rubin vase illusion is a famous example where the same image can be seen as either a vase or two faces in profile. This illusion demonstrates how our brain can switch between different interpretations of the same image. These examples highlight the intriguing nature of reversible figures or ambiguous images and their role in the field of psychology as research tools. They challenge our brain's ability to interpret visual information and provide insights into the complexities of perception. Thank you for watching.